In this video, I'm going to run through an example of using Nastran design optimization, which is SOL200. In a previous video, I showed how to set up the mesh on my steel mountain bike frame. Today's goal is to optimize the geometry of the top tube. To save some time, I've already created a load that simulates an impact on the front wheel. To do this, I created an RBE3 element with the dependent nodes on the head tube of the frame and the independent node at the center of the front wheel hub. I have applied a force of 270 pounds in the horizontal direction. The first thing I'm going to do is to switch the top tube property to use a Nastran beam that will write out a P-beam L, and I will explain this a little later when I create my design variables. In my previous video, I used the tube centerline command, which finds the radius and thickness of the tube and then uses that to calculate the section properties to write a P-beam. So I've already created my Nastran beam property for the top tube, and I made it ID 100 just to make it stand out a bit more. And the Nastran beam is built off of two dimensions. So dimension 1 is the outer diameter and dimension 2 is the inner diameter. And so now I'm going to switch my top tube elements to be the Nastran property using modify, update elements, property ID. I'll use the method onCurve and select my top tube curve there. I can see it grabs all the elements, and I'll switch it to the Nastran top tube property. So now you can see when I highlight these, they're all good to go. So now I'm going to set up my design variables for my top tube using model, optimization, variables, and topology regions. I'll click the new button and I'm just going to use the type to property. You can see there's some other ones in there, but again, I'm using property. Now I'm going to switch this to my Nastran top tube property, and I'll leave it to dimension 1, which is the outer diameter. And I could do ranges here, like set the minimum to, maybe 0.45. Instead, I'm just going to use the percentage. Or I can do 75% of the original value, and then the max will be 125% of the original value. So you can see the values there on the right. And again, I'm going to do the same thing with the Nastran top tube, but this time dimension 2, which is the inner diameter. Change it to percentage and do a minimum of 75% and a max of 125%. So the reason I switched to a Nastran beam is because I can create variables based on the tube dimensions. And if I were using a P-beam like it originally was, I would have to create variables based on the area of the cross section or moment of inertia about specific axes. And this would make it a little bit more difficult for me to back solve to find the tube shape after it's optimized. So now I'm going to go create some limits for my design using model optimization limits. And I'll create a new one here. I'm going to use element stresses. And more specifically, I'm going to start with beam end A max combined stress. So I'll select that one. And then for my entities, I'll just use the property and select my Nastran beam elements. And I'll leave the lower bound at 0, but my upper bound will be 65,000 PSI, and I'm going to use some kind of safety factor, so I'll take 60% of that limit there. And then I'll go ahead and basically recreate this same thing using beam end B max combined stress, and that way I just don't have to worry about the way my elements are oriented. So if one comes into a joint where it's mitered, I don't have to worry about it being end A or end B on the beam. So same thing, 65,000, 60% of that, hit OK. And I'm just going to scroll over here to see what my lower and upper limits. Again, lower was 0 and upper is 39,000. So now I've created everything I need. I can start setting up my analysis. So I'm going to go into the analysis manager. I still had the one from my modal run. So I'll click new and I'll drop down the analysis type to number 8, design/topology optimization. So I'll click through a couple of these dialogues until I get to the Nastran optimization options. By default, it's set to design, and that's what I want here. Topology would be more for if you're optimizing the shape of an object. My goal here is to minimize weight. So by default, that's fine. And again, with the variables and the limits I've created, I wanted to minimize the weight within the bounds of those variables and limits I've created. Cycles by default is 25. That should be fine. This is a relatively small model. I don't expect it to take that many cycles. If you had a larger model, you may need more cycles. Again, this is kind of varying on the size and maybe how many load cases there are. And I'll go into select optimization variables, and I'll just check both of the ones that I had created before. So again, I'll kind of skip through a couple of these dialogues until I get to the optimization limits, and I'm just going to check off both of those limits that I created about the end A and end B max combined stresses. And I'm just going to go in here to my boundary conditions and make sure that I have my load and constraint selected. And I just want to point out that I could do as many load cases as needed. But again, this is just an example, and I'm trying to cut down on complexity here. So I'll kick off the analysis. So I'll skip forward a little here until my results are read in. And you'll notice that a couple functions have been created in my model. So I'll go ahead and plot the first one, the design objective, by right-clicking and hit show in charting. And this model only took 6 cycles to solve, so it's pretty quick. Again, a small model. And you can see that each cycle it reduces the weight and then solves again and so on. So now I'm going to show design variable 1, which was the outer diameter of my top tube. And likewise for design variable 2, the inner diameter of the tube. So I can kind of see, as each cycle progressed, the dimension that it calculated. So now I'll go into my data series manager, and I'm going to add both the top tube and down tube to the chart so I can kind of look at these together. And the difference between the 2 points would be the thickness of my wall. And so what I'm going to do now is take the data from my charting pane and send it over to Excel. So I'll drag Excel onto my screen here. And what I want to do with this is basically just calculate the thickness of the top tube. So the light blue line is my outside diameter, and the green line is my inside diameter. So I'll take cycle 6, which is the final and best cycle. I'll take that dimension from the outside diameter and subtract it by cycle 6 of the inside diameter to get my thickness. So I'm going to click out of Excel and my charting pane, and the last thing I want to do is show a contour plot. So I'll go into my post-processing tab and turn on contours and switch to beam end A max combined stress, because again, this is what I used for my design limit. And right now I'm showing design cycle 0, which is like the original static case, and I see a max stress of about 35,000. So I'll switch to design cycle 6, which is my optimized structure, and I actually see a max stress of 39,000. So what that tells me is that my original model was actually over-designed. So as the solver was iterating and changing the dimensions of the top tube, it was reducing weight at the cost of increasing stress. But that is okay because it is still well under the tensile limit because of the safety factor I added earlier. So thank you guys for watching. If you have any questions, please feel free to leave them in the comments. My goal here was to just show an example of using Nastran design optimization in Femap, so I hope this helps.